Hello. In this section, in this video, we're going to look at trigonometric identities. And I'd say if you started this chapter from when you seen this chapter 10, the first two parts are a little bit pointless because you just put it on the calculator. But this is where I think you really need to pay attention with this chapter. It's quite an important concept that comes up. But anyway, trigonometric identity then. So let's cast back to when we looked at the unit circle earlier on, and I'll remind you, we draw our axis. Then the unit circle is a circle radius 1, and we make it in the origin the centre, right? So it looks a bit like this, right? So that'd be 1 there, that'd be 1 here. Well, this would be -1 down here and -1 there. So the whole idea is that then every point, say point P here, from the centre, the origin, has to have a length of 1 because it's the radius, right? Right, so, and then consider it makes an angle of theta by the x-axis, right? And so if I then, say, draw this triangle out, right? There we are. Then you have the point P up there, and then the origin there, which is the centre of the circle. Now again, the length here would be 1. That's the radius, right? That length there. And we have the angle theta, right? Now, then we have the right angle here. And then obviously this would be the hypotenuse, right? This length of 1, because it's opposite the right angle, right? And because this side is facing the angle, this would be the opposite side, and then this would be the adjacent side. Now, this point P then as well would have an x and y coordinate, right? Just, I don't know what it is, but it's just an x-y coordinate. Now, if I then draw a line here, this would be the x coordinate, and then that'd be y up, right? So we can also say this is going to be x then, this length there, and the y there. Okay. Okay. But then we can use SOHCAHTOA then to express, we can find x and y. So firstly, we can find the sine by using SOHCAHTOA. So opposite is y. So therefore, we would have sine theta is y, which is the opposite. So the opposite over hypotenuse, right? Remember your SOHCAHTOA. But the opposite is y, and the hypotenuse is 1, right? Well, therefore, y over 1 is just y. So therefore, y is sine theta. So we can literally just call this sine theta, that length. Okay, and also same for x then, we can do cosine of theta. Which should be the adjacent over the hypotenuse, right? Again, remember your SOHCAHTOA. Adjacent is x, and the hypotenuse is 1 again. Oh. Well, that just goes to x then, so therefore we can say x is just cos theta. Cool. Okay. So we could say that this is cos theta. Now, we can then, what else can we do with this triangle? Well, firstly, I notice because it's a right angle, I can do Pythagoras, because now I have all three sides, right? I have cos theta, sine theta, and 1. Well, if I do Pythagoras theorem, remember, as 1 is the hypotenuse, that'd be 1 squared equals the other two sides all squared. So this side, firstly, is sine theta, which is y. So that'd be sine theta squared, which we'd call sine squared theta. And then the other side is cos theta, the x, right? So then that'd be cos squared, right? If you square both sides. So that's Pythagoras then, right? The hypotenuse squared is the opposite and the adjacent all squared, then added together, right? So we get this equation then. Well, 1 squared is just 1, right? So therefore we can conclude that sine squared theta and cos squared theta is identical to 1. Okay, so that is the first identity we will be using, and it's identical to 1 because it's true for every value of theta. Because this point P could be anywhere along the circle. We could have put the point P there, we could have put the point P there, we could have put the point P there, and the whole idea is we can keep drawing triangles, right? We can draw angles of theta there. Oh, that would be theta there. Obviously the length would be 1. All the lengths would be 1 because they're on the radius, right? They're on the circle. So it doesn't matter where our point is. It'd be true for any value, right? It'd be true for any point on the circle. This would all our working we've done here would be true for every point on the circle. So this is true for every value of theta then, right? This identity here. And remember when we talked about identities, an identity is a statement that's true for every value of theta, or every value of what we have, right? So in this case, every value of theta, any angle, this identity will always be true. Okay, sine squared and cos squared is identical to 1. Okay, okay, so that's Pythagoras, but also I left out tan theta from this. We can still work out tan theta as well. So we can also say that tan theta is going to be the opposite over the adjacent, right? So I'm going to say and tan theta is opposite over adjacent. But then if we go back to our triangle up here, the opposite is sine theta, as we discussed. We've got y and x there. So we've got sine theta for the opposite, and the adjacent side is cos theta. So the opposite over adjacent is sine theta over cos theta. And again, that has to be identical, right? Because this will be true for any value of theta, right? Because because any point in the circle, this would work, right? This tan theta, we can construct that triangle. So there we are. So we've got this next identity as well. Okay. So tan theta then is also identical to sine theta over cos theta for any angle theta. So there we are then. So these are the two identities we will be working with in this section, and indeed in the first year. We will look at more identities in the second year. But there we are. So if I'm going to restate it then, we firstly have sine squared theta and cos squared theta is identical to 1, and tan theta is identical to sine theta over cos theta. Okay, we will be using these two identities throughout this section and throughout this video as well. Right, okay, now unfortunately you do need to remember them or memorize them in some way because they're not in the formula book. Okay, but you do not need to know how to prove them. You just need to know how to use them. Okay, via the specification. So you don't necessarily need to learn what we've done up here. I'm just showing you how we get to the identities, but you do need to learn them. You need to memorize them, but you just need to know how to use them once you learn them. And once you do learn them, they do seep into your memory once you do more and more questions, right? So it's not as bad as it might seem. So so this is the idea. Then we're going to use these two identities in this section. Now, lastly, about identities in general. What we're going to be looking at is proof. Say for example, again, when we looked at this in chapter 7, I think, when we looked at proof. But say if we had x squared. Minus 2x minus 3, I can say this is identical to x plus 1 x minus 3. I believe, yep. I can say that it's identical, meaning the left hand side of the inequality of the identity is always the same as the right hand side, so they're equivalent. These two expressions are equivalent. That's what they're saying, okay, when we use the identity. So when we want to prove an identity, so if we want to prove this actually is true, obviously we've got a left-hand side and a right-hand side. What we need to do is, we need, so when with proving identities, and we will be doing that in this section, so that's why it's relevant. With proving identities, we need to show. We need to show, yes, that one side is the same as the other. Okay, obviously it seems a bit like, well, obviously, but what I mean by that is, we have to, when we want, if we want to show that the left hand side, say here, is identical to the right hand side, we can only work we can only work with one side, okay? So if we wanted to prove this inequality, well, you could either factorize the left hand side or we could just expand it, right? If we expanded the right, what we need to do basically is say that x plus 1, x minus 3, firstly, is identical to, if we were to expand this, it would be x squared minus 3x add x minus 3, and then we can simplify, right, to x squared minus 2x minus 3. And there we are, right? So that is now the left hand side, okay? So we can say the right hand side, RHS, is equal to the left hand side, or identical to the left hand side. And that's how we're going to do these proofs, right? We're going to work with one side of the identity, and then we're going to do some maths and simplify it until we get to the other side, right? And that's what we'll be doing right in this section. But I'll just give a brief overview of the idea of an identity. But yeah, okay, let's have a look at some examples then. And bear in mind we will be working with these two identities here. Right, okay, we need to simplify the following expressions. So firstly, we have sine squared 3 theta and cos squared 3 theta. So I'm going to rewrite our identities again, right? These two identities. Okay, and we're going to need to use them in these questions. So firstly, this one then, sine squared 3 theta and cos squared 3 theta. Now, hopefully, it's kind of ringing the alarm bells that it looks very, very, very similar to this one, right? But you're probably thinking, well, there's a theta there, but I've got a 3 theta. Hang on, what do I do? Well, it's the same, right? 3 theta is still just an angle, right? Really, I could say like I could just say like theta is, I don't know, 3x, and then I'd sine squared 3x and cos squared 3x equals 1, and then that's the same thing, right? The idea is that the angle is the same in both the sine and the cos, so we can still apply this, right? This would then still go to 1, okay? And there we are, okay? That whole expression just goes to 1, okay? And that's it. So that's by applying the identity. Okay, so I'm going to say by applying okay, there we are. I could say sine squared x and cos squared x, and then you could then say if x is 3 theta, then we would get sine squared 3 theta, and cos squared 3 theta gets me 1. Okay, so the whole idea is with this particular case equation, don't get thrown off. The angles look a bit different. 3 theta is still an angle, right? But there we are. Okay. Okay, part B, we then need to show that we need to simplify 5 minus 5 sine squared theta. Now, again, we have a sine squared here. So I'm thinking I want to use this identity here. But how exactly? Well, we can also sort of rearrange these identities, if we need to. if sine squared and cos squared theta is 1, we can also say that therefore, if we subtract sine squared to both sides, we can say that cos squared theta is also identical to 1 minus sine squared theta. So you can add and take away, like, sort of both sides of the identity, right? Like an equation, right? So we can say this, right? We can rearrange that identity, the sine squared cos squared is 1, into this, right? To cos squared is 1 minus sine squared theta. Well, hopefully then that kind of this part, the 1 minus sine squared, resembles quite closely this expression here. But it's just 5, right? I can factor a 5 out, right? So I can say this is identical to 5 lots of 1 minus sine squared theta. Oh, but hang on, 1 minus sine squared theta. That's what we got here. But we also know that this is cos squared theta. So then I could substitute that in. Substitute that result in. So then this is also identical to 5 lots of cos squared theta. And there we are. That's about simplified as we can get it. But there we are. So then this expression then is identical or the same as 5 cos squared theta. Okay. Cool. Part C then, I'll do it down here. We have sine 2 theta over root 1 minus sine squared 2 theta. Now again, what can we do? Well, we can't do anything with just this sign, right? Not really. But this, again, this 1 minus sine squared looks very, well, it's this, right? It's this 1 minus sine squared theta. But obviously now, the angle's now 2 theta instead of theta. But again, it's just the angle, right? The angle's the same, so we can still apply that same identity. So we can say that this is also the same as sine 2 theta over the root. And we know that 1 minus sine squared theta is just cos squared. So this is cos squared of 2 theta. And there we are. Well, then, this is a square root of a square, right? We have cos squared, right? By the way, cos squared 2 theta is the same as just cos 2 theta all squared. That's the same, right? It's just that with trig functions, we put the 2 for the squared, or if we had a 3, a power 3, a power 4, whatever, we put it before the angle, not after the angle like that. That's saying cos of 2 theta squared. Okay, they're different things. But when we raise it to a power, we usually notate it in that way. But it's the same as just raising the whole thing to a power 2. Anyway, so this is a squared of cos. So if we square root in a square, that's just cos 2 theta then, right? And there we are. So we got to that point. Okay, well then what can I do here? Well, let's have a look at the other identity then. Well, this tan theta is sine theta over cos theta. That's what we got. We got sine 2 theta over cos 2 theta. Right, again, the angle's 2 theta, not theta. But again, the idea is the same, right? That we have sine over cos of the angle. So then we can say that this is then tan 2 theta. And there we are. So that's about that's fully simplified now. Okay. And there we are. So that is literally the whole idea with identity proof. They can be quite tricky to do first time, but once you practice some more questions. By the way, I do with every video, I do recommend you practice some. Maybe pause the video and do a question yourself if you feel confident, or find some other questions in the textbook or otherwise. But once you practice them yourself, you start to get the hang of it, right? But hopefully that's the whole idea, right? We're going to just simplify, try and substitute these two identities in wherever we can, okay? And eventually we get to a simplified answer. Okay. Now we've got this example. Okay, we want to prove that this whole fraction is identical to 1 minus tan squared theta. Now, this is where the talk I did about the inequality stuff at the start will come into play here. So I'm going to rewrite this, restate it. Sorry, sine to the 4 theta over cos squared theta is identical to 1 minus tan squared theta. Now, this is the left-hand side, right? The one side of the identity, and this is the right-hand side, which I denote LHS and RHS, right? That's what they stand for. You can shorten it in that way. The examiners will know what you mean when you use LHS, RHS. Anyway, so the idea is then to prove this identity, we need to prove that one side is exactly the same as the other side. So we need to simplify either side, and then we get the exact other side eventually, right? We could either somehow deal with 1 minus tan squared theta, and then we get this fraction in eventually. But the strategy is generally to pick the more sort of complicated side, the side with the more weirder terms in. So this whole weird fraction, this big fraction, it's better to work with the more complicated stuff, because then you can simplify it down into the more simpler term, right? It's a lot easier to simplify a more complicated term than try to complicate a simple term to make it more complex. Right, so so I'm going to work with this side then, and I'm going to try maybe use my identities or other tools that I know to get to this exact state, this expression here, 1 minus tan squared, okay? Right, so let's start with this then. So we're going to start with cos 4 theta minus sine to the 4, well, that's a power of 4, by the way, okay. Cos to the 4 theta minus sine to the 4 theta over cos squared theta. Now, then we're going to just do a chain of like identities, right? So what can we do? And we're going to just try and simplify this as much as we can, and then we get to this point here. Right, so what can we do here? Well, we can't do anything with the cos squared. You might think maybe we could split up the fraction. You could do that. And try go from there. But what else can we do? Well, a very good tip. A lot of these identities are going to involve fractions. That I find anyway. In exams, they often will involve a fraction of some sort or whatever. A very, very good tip I'll give is, and I write that here somewhere, tip, is to try and factorise whenever you can, okay? And actually, I'll say that here because we can actually factorise the numerator. Because if I said that cos theta is x and sine theta is y, well, cos to the 4 theta minus sine to the 4 theta is just x to the 4 minus y to the 4. Hopefully you notice this is a difference of two squares, right? This is then going to be x squared minus y squared and x squared plus y squared, right? So yeah, so then if we say x is cos theta and y sine theta, well, this factorises then in this way. So then we can say that this is cos squared theta minus sine squared theta, and cos squared theta plus sine squared theta, all over cos squared, okay? And I remember we did look at factorising expressions back at the very start of the course. So there might be some good exercises in that section if you want to practice your factorising. But anyway, we've got to this point. So again, look at our factors then. Well, cos squared minus sine squared, I can't really do much about. But what about this? Cos squared theta add sine squared. Well, if we go back to our identities here, well, isn't sine squared theta and cos squared theta just one, right? The first identity. So actually, this whole factor then just goes to 1. So we're just simply left with cos squared theta minus sine squared theta all over cos squared theta. Right. Now we could factorise again, because this is another difference of two squares. We could perhaps say that's like what? Cos theta minus sine theta. and then cos theta plus sine theta. But the problem is we can't really simplify either factor, unlike this factor here, because it was cos squared and sine squared, which went to 1. None of these two factors really simplify in any way, so factorising won't get us anywhere at this point, that I can spot anyway. What we can then do is what I said earlier, we can then kind of split up the fraction, and I notice things will now cancel, because I have a cos squared over a cos squared minus a sine squared over a cos squared of theta. And this cancels, right? This cos squared over cos squared. That's just 1. And then I have minus sine squared theta over cos squared theta. Now, if I said that this is just sine theta over cos theta all squared like this, hopefully you can spot what identity we can use here. Well, hopefully again, if you remember, if you look back to our identities, we also know that tan theta is again sine theta over cos theta. Well, then sine theta over cos theta is a tan theta. So this is 1 minus tan theta all squared. And then we can just say that's 1 minus tan squared theta in that way, okay? Well, then there we are. Then we got to showing 1 minus tan squared theta there. So we're done. So we proved the inequality, the identity, sorry. I don't know why I say inequality, but that's the identity proved, right? Because now we've shown clearly that we started from one side of the inequality, so the left side, and then we got to the other side, right? At the end. So both sides have to be the same, okay? And there we are. So that's the whole idea, right? Is we work with one side, and then we do some manipulations, some simplifying, and then we get to the other side. Very often by substituting some of the identities we know, right? So the sine squared cos squared is 1, and tan is sine over cos. Right, okay. Okay, let's have a look at this example then. We are given that cos theta is minus 3 over 5. We need to find the value of sine theta. And I should probably say it says the exact value as well, okay? No decimals, okay? But yeah. So cos theta is minus 3 over 5. Now, when we looked at in the last section with triangles and the cosine rule and stuff like that, you might be inclined, fair enough, to say, well, just do inverse cos, right? So then theta is inverse cos of minus 3 over 5, right? If you do that in your calculator, you'd get this 126.869, blah, blah, blah. But then 2 problems. First of all, theta is reflex, so we'd have to find another solution by perhaps considering the cos graph. So 126 would be about there. So then the next solution would be about there, right? Now we can find that. That's not a problem. We could find this other. So if this was 126.9, we could find the other solution there by the symmetry. We will look at that in the next few videos. But that's one problem. But the other big problem is often they want the exact value, which you can find. The problem is this is a long, never-ending decimal for the angle. If then your instinct was to then say sine theta after that by doing sine of this 126.8669, we would get an answer that's very, very close to the answer, right? But it'll be a bunch of decimals, right? We can find a way to avoid finding the angle and having all these decimals, right? Which will give us a non-exact answer. And this is where the identities will come in then. So we're not going to go that way then. What we're going to do is we're going to recall again that the identity sine squared theta and cos squared theta is indeed 1. Right. And now what this does is it gives us a way to calculate or gives us a relationship between cos and sine without having to find the angle, right? Without having to do inverse cos or inverse sine. So what we can say then is, if cos theta is minus 3 over 5, that therefore that cos squared theta, if we square both sides, is going to be positive 9 over 25, right? If we square minus 3 over 5. Now we can substitute that into here to get a value for sine theta then. So therefore sine squared theta add cos squared, which is 9 over 25, is also identical to 1. So then we can say that sine squared theta, well, it's going to be then 1 take away 9 over 25, right? If we take away 9 over 25, right, to both sides, if we do that, then we get sine squared theta is 16 over 25. Right, but that's sine squared theta. Then if we want sine theta, then we're going to square root both sides. And it's going to be plus or minus root 16 over 25, which should get me 4 over 5, right? If we do that root, 4 over 5 there. And again, it's plus or minus because we're solving for something. So remember when we're solving, like, for example, x squared is 1. We'll just say x is either plus a 1 or minus 1, right? So plus or minus 1. So yeah, we are solving for sine theta here. So we do need plus or minus. Now, so either sine theta is 4 over 5 or sine theta is minus 4 over 5. Which value do we take then? This is where this will come into play. Theta, the angle we're told is reflex. What we can do at this point then, I'll make a note then, theta is reflex. What you can do then is consider the sine graph, right? Say between 360 degrees, right? The standard sine graph. Now, if theta is reflex, that means it has to be between 180 and 360, right? That's a reflex angle. It's above 180, right? So that's going to be concerned with this portion of the sine graph, right? Where this, let me draw that again. There we are. Where this is 180 there, and this is 360. Well, between 180 and 360, well, that's the negative part of the sine graph, so it has to be negative. So I'm going to say, as theta is reflex, then sine theta must be negative. So the value of sine theta, okay? Because it's on the negative part of the graph between those two angles, right? But then that means we have to take minus 4 over 5 then, right? So therefore, sine theta is minus 4 over 5. Okay, and by the way, I just want to highlight another flaw if you decided to just find the angle theta. Now, recall we got this situation where sine theta is 4 over 5 or minus 4 over 5. If you put that in the calculator only gets you one value, and actually it gets you 4 over 5. Let me show you. So again, if we were to find cos theta, which is minus 3 over 5, if we did inverse cos, right, on that again, we'll get the answer 126.869. However, if we then put that into sine of this, put that angle in your calculator, it gets you, and surprisingly my calculator just gets you 4 over 5 exactly, but that's still wrong, right? Because remember, sine of the angle was not 4 over 5, we got minus 4 over 5 as our answer. And so the calculator will only always give you one value, right? In this case for sine theta or anything else, right? And actually we do need to consider the second one, and it was minus 4 over 5. The reason being is because what the calculator will only consider like the closest answer. So, for example, if we then, for example, cast yourself back to when we did the ambiguous case with the sine rule, right? Say if we had sine theta is a half, so therefore theta would be 30 if you did it on the calculator. But there'd actually be two solutions to here for sine theta. If we did the sine graph, 13 would be let's do it here between 180. 30 would be there, so then the other solution there by symmetry would be 150. So the other solution is 150, but the calculator only gives you one angle for theta. Okay, the reality is there are multiple values for the angle, but the calculator will always only give you one, and not necessarily the correct one. All right, depending on the question. That is why you have to use this method instead, right? Using the identities, right? Because because we might have multiple angles, and therefore it makes it a bit tricky. And the calculator, if you just put the angle in, as you saw here again, it won't get you the right answer to the problem. Okay, so you do need to be a lot more careful. So therefore, we need to use the identity, right? So do try to avoid using the identity, just finding the angle. When if we got the cos of it to find the sine of it, try not to just find the angle, okay? But yeah, so just be careful if you just use the calculator solely for this question, right? No, don't try and find angles, okay? Cool, then part B, how much room do I have? Okay, part B, very similar now. We have sine alpha is 2 over 5, and alpha is obtuse. Calculate the exact value, see again, exact value of cos alpha. Okay, we have sine alpha is 2/5. We need the value of cos alpha, not the value of alpha, the angle alpha, but just cos of the angle. Okay. So again, if we did inverse sine to get alpha, the angle, we would get a nasty decimal. So to avoid that, we can say, well, the identity again, right? So sine squared of alpha add cos squared alpha is again 1. Remember, you must know that identity. We will be using it again and again. So then we can sort of square both sides, right? Well, square sine, sorry. So sine alpha is 2/5. Therefore, sine squared alpha is going to be 4 over 25, right? If I square that fraction. Okay, so then I can sort of substitute that into this identity then. So then I can say 4 over 25 add cos squared alpha is 1, right? And then I can subtract 4 over 25 to then say that cos squared alpha is 1 minus 4 over 25, which is 21 over 25. And therefore then, if I square root both sides, I get that cos alpha is going to be plus or minus root 21 over 25. If I put that in a calculator, that simplifies to plus or minus root 21 over 5, okay? So again, that is an exact answer. It's not a nice answer, but it's exact. There's no decimals, right? I think if we were to plug in the value of the angle, if we found the other method of just finding the angle alpha, then substitute that into cos, we wouldn't get that. The calculator most likely wouldn't spit out that exact answer. It'd probably give you a nasty decimal, right? So this is why we do need to consider this idea, this identity. Anyway, so we get to this point then. Now, again, so that means we have two possibilities. Either cos alpha is plus root 21 over 5 or minus root 21 over 25, or 5, sorry. So again, which one? Well, we were told information about the angle. It's obtuse. So, again, we're going to consider the same sort of idea then. So alpha is obtuse, which means it has to be between 90 and 180. So again, we're going to consider the cos graph to help us here. So the cos graph looks like this. So if it's between 90 and 180, well, 90 is going to be there, and 180 is going to be there. So again, this part of the graph between 90 and 180 is below, right, the axis. It's negative, right? That means then we need a negative answer for cos. So I'm going to say alpha is obtuse. So I'm going to say alpha is obtuse. Therefore, cos alpha must be negative. As if it's obtuse between 90 and 180 again, that part, the cos graph is negative, right, on the negative y-axis, right, underneath the axis. So therefore we have to take this then. So cos alpha then is minus root 21 over 5. And there we are. Job's a good one. So there we are then. So again, these identities also give us a way to link sine and cos together, right? Without having to do inverse to find the angle. We can just skip to converting cos to sine, right? Via this formula here. Identity then, over there. Okay, let's have a look at another example. Okay, we are told P is 3 cos theta and Q is 2 sine theta. Show that 4p squared and 9q squared is 36. Right, again, it's sort of like an identity. Again, obviously it's an equation, but what we can do then is consider 4p squared and 9q squared and see what I get, and hopefully I get 36 if I simplify it. Well, P is 3 cos theta, so I can sort of substitute that in, right? So this is identical to 4 lots of 3 cos theta, and then add 9 of q squared, so that'd be p squared, sorry. And then 9q squared would be 9 lots of 2 sine theta, all squared there. And then we can sort of expand the bracket, right? Well, that's going to be 4. And then if we do 3 cos theta squared, well, remember, 3 cos theta squared, it's the same, it's times in by itself, right? So that's going to be the same as 3 cos theta, lots of 3 cos theta. And then hopefully you can spot, well, 3 times 3 is 9. And then cos theta times cos theta is cos squared theta. There we are. And then if we do 9 and then expand this bracket, well, 2 sine theta all squared is going to be 2 sine theta times 2 sine theta, which is 4 sine squared theta. And then we can expand this, right? Expand the brackets we have. So 4 times 9 is 36 cos squared theta. And 9 times 4 is, again, 36 sine squared theta. Well, hang on. If I then factorise the 36 out, 36 lots of sine squared theta, add cos squared theta. If I get rid of this, hopefully you can spot then that we have the identity, right? Sine squared and cos squared is 1. This whole bracket goes to 1 then. 36 times 1, which is 36. Well, there we are then. We get 36. So cool. There we are, and I'll make a note then as well that sine squared theta and cos squared theta again is 1. Okay, that's what we used. There we are then. Okay, let's have a look at some more questions then. We are told that this diagram has triangle PQR with the length PR is 8 and the QR is 6, and angle QPR here is 30. We need to show that sine of Q, so the angle at Q, which is going to be here, I'll call that theta. The sine of the angle is 2/3. So how are we going to find that then? So how are we going to find the sine of this angle then? Well, hopefully you can spot, this is going to link back to what we did last chapter with the sine rule, right? So we've got a triangle when we've got 2 angles and 2 lengths we're dealing with, right? It's going to be the sine rule. So we can say then, by the sine rule, that firstly sine theta, which is angle at Q, right? Sine theta, which is opposite the 8, so it's going to be over 8 then, is going to be the same, equal to the other angle, sine 30. And that 30 is opposite the 6, so it's going to be over 6. And then we could just sort of simplify for sine theta, right? So then I could say that sine theta is 8 times sine 30 over 6. And then I could just put all that in the calculator, right? So then sine theta gets me 8 times sine of 30 over 6. Gets me 2/3. And there we are, that's part A done. Part B then, we are told that given that Q, the angle theta again at Q is obtuse, find the exact value of cos of the angle. So cos theta. Now, we found sine theta, so we then need to find cos theta. Right. So that's going to go back to the stuff we looked at in the early example, where we're going to use cos squared and sine squared is 1. Now again, if we were to invert, if we do the inverse, right, to find the angle theta, well, firstly, you'd have the ambiguous case, right, where if we did inverse to get sine to get theta, theta would be firstly from the calculator you would get 41.81031 blah 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 degrees. But then there'll be another possible angle for theta, right? So if we use the sine graph, right? Remember when we did the ambiguous case to get the second possible angle? So if 180 is there and 0 is here, if 41 is say there, 41.8, then the other angle, the other possible value for theta would be 180 take away, right? This angle. Which would get me, if I put that in the calculator, 138.189 blah blah blah. And actually that would be another legitimate valid solution, because if I added this angle 138 with 30, I'd get 168 point something. That's below 180. So again, angles in a triangle have to add up to 180. So we obey that. Look, though, we obey that rule, right? Because this would also give us a valid angle, right? So we've got two solutions for theta here, and again we have another problem then. Not only are the angles just ongoing, right? They're just decimals forever, but there's two possible values of the angle, which complicates things even more, because finding cos of it might be a bit trickier. So what we're going to do instead then, because it's very tricky then, just trying to find theta and then substitute that into cos to get an exact answer, we're going to do the same method then, right? So I'm going to ignore this. I'm going to say that's probably the pitfall a lot of students would go for, just finding the theta, doing inverse sine, and then substituting that into cos. But do not do that, because we can do things a lot more straightforward and just try and use the identity, right? So we're going to record again that sine squared theta and cos squared theta is 1. And we know that sine theta is 2/3. So therefore sine squared theta is going to be the square of 2/3 squared, which would be 4/9. Right, and then I can substitute that into there, right? Into the identity. So then I'm going to get 4/9 add cos squared theta is 1. And then I can just rearrange for cos, right? So cos squared theta is going to be 1 minus take away 4/9, which is 5/9, is it? Yes, 5/9. And then I can just square root both sides, right? So then cos theta is going to be plus or minus the root of 5/9, which simplifies to plus or minus root 5/3. Okay, so then I've got two possibilities again. So either cos theta is positive root 5/3 or negative root 5/3. Okay, which one do we take? Well, we need to consider the angle, right? So Q is obtuse, right? The angle is obtuse. which means it's going to be again between 90 and 180 degrees, right? So to help us consider what sign of cos to take, let's consider the cos graph. I'll do it up here. There we are. So between 90 there and 180, which would be there, well, that part of the graph then is again below the y-axis. It's below the axis, right? It's underneath, right? The graph is underneath. So it's in the negative part of the graph, right? So it has to be negative then, right? So I'm going to say, as theta is obtuse, cos theta must be negative. Therefore, then we take the negative solution. So then cos theta, the value of that is minus root 5 over 3. And there we are. Okay, cool. And again, if we were to do the, if you did invert and find the angle, I don't think you'd get the answer from the calculator, because if you put in a decimal, I don't think it would spit out that exact answer. So to get the exact answer, we do need to use this identity instead, right? To find a causal sign, okay? But there we are, okay. And we've got one final question, exam question here. And it's not easy, I will say it's not easy. But we've got an exam question to finish off. But we need to show that 1 over cos theta plus tan theta is identical to cos theta over 1 minus sine theta. Right. So again, we need to pick a side to work with, the left side or the right side of the identity. I'm again thinking the left side. Now, a general tip is usually the left-hand side. The left-hand side is usually the side you want to pick to simplify things, to get the other side. Usually, right? Obviously, there's no. That's just from what I spot anyway. But I wanna start with the left side anyway, because I notice I can perhaps add these two to combine it as one fraction. It's a lot harder to split up a fraction in this way, because obviously we have 1 minus sine theta. We can't split up a denominator, right? Only a numerator. But anyway, we can. It's a lot easier to combine this side as just one fraction by adding them together, right? So I'm going to start with that then. So we have 1 over cos theta plus tan theta. Right, okay. Well, actually, can I not also express tan theta as a fraction? Because tan theta, remember, is also sine theta over cos theta. So I can say that this is identical then to 1 over cos theta plus sine theta over cos theta. And again, another sort of tip is to convert a tan into sine and cos. The fewer things you got to work with, so only sine and cos, they're kind of easier and a bit more obvious of how you need to proceed, right? But anyway, so we split up this, we converted tan theta into sine and cos theta, right? So now we've got a fraction. Well, actually, we've got a common denominator, right, of cos theta, so we can just simply add the top. Then it's 1 plus sine theta over cos theta. Now, remember, the aim is we need to get to cos theta over 1 minus sine theta. That's the fraction we need to end up with. Well, it's very awkward. It's kind of the other way around. Instead, we've got 1 plus sine theta over cos. It's like the fraction's kind of flipped in a way. Obviously, it's not completely flipped because we have one minus there. We have 1 plus sine theta. Right, so I think this is the tricky bit, right? How do we get to the next stage? Well, I think you can kind of force trying to get this answer, because I recognise that cos theta is on the top here, on the numerator. What if I just times top and bottom by cos theta over cos theta, right? I can times both sides of both top and bottom of a fraction by the same number, right? And then I immediately then get a cos theta on the top of the fraction, right? So I can kind of force the answer in that way. So if I do that then I get cos theta, lots of 1 plus sine theta, all over cos squared theta. Well, actually, this is kind of good now because cos squared, remember our denominator also only it kind of looks like 1 plus, if we had sine squared theta and cos squared theta is 1, I can rearrange to get cos squared theta is 1 minus sine squared theta. Doesn't that look vaguely similar? Obviously, it's just sine theta, not sine squared. But I can kind of convert the cos squared theta as just 1 minus sine squared, right? To get a sine out of it, right? I want a sine out of the cos here. So that I can do that then. I can substitute that identity in. So I'm going to say that cos squared theta is 1 minus sine squared theta. So then I'll substitute that into here, the denominator, to get cos theta, lots of 1 plus sine theta, all over 1 minus sine squared theta. Now, remember my tip earlier, I said to try and factorise whenever you can. Well, now I can. This is actually a difference of two squares, right? I can factorise the 1 minus sine squared theta into 1 minus sine theta, or 1 plus sine theta, right? Because remember, 1 minus sine squared theta, well, it's almost like 1 squared minus sine squared theta. So if I did the difference of two squares, that would then be 1 minus sine theta, 1 plus sine theta. Remember, you do need to start being able to recognise. It will help to spot a difference of two squares with like more weird out awkward terms like this. So even with trig functions, we can do difference of two squares to factorise it, right? Again, it's something it becomes more natural and easier to spot when you do more examples. But anyway, we can factorise the 1 minus sine squared in this way. Well, and then we can cancel some factors out, right? 1 minus sine theta is common on both top and bottom. So I can cancel that out, and I'm left with then cos theta over 1 minus sine theta. Well, then there we are. That is now the right-hand side. So we're done. The proof is done. So therefore we can show that 1 over cos theta plus tan theta on this side has to be equivalent or the same as cos theta over 1 minus sine theta, because that's what we're showing, right? We simplified it to this. And there we are. Cool. So yeah, so that is a very, I think that's a very hard trig, harder than usual, I'd say. Sort of trig proof question, identities with trigonometry. Very tricky that is. A lot. Basically, you combine everything into one question there. Like we factorise difference of two squares. We used both identities. We added fractions. We cancelled stuff out. We even we did a lot of stuff there. But hopefully, kind of spot what we do. But like I said, practice makes perfect. But yeah, this is an important topic. It does come up quite a lot, especially in year 2. But yeah, but that's the whole essence, right? Remember these two identities here. Yeah, you do need to remember them. But hopefully, when you do more questions and you keep remembering and keep substituting these four identities in, they start to seep into your memory, right? So it becomes kind of like second nature. You don't have to force you to have to memorise them. But yeah, you do need to learn them. They're not in the formula book, so just be aware. But you need to be able to apply them to prove other identities like this one, right? But yeah, so that's the whole essence, right? With identities, we work with one side and then we eventually get to the other side and we show that they're equal, okay? But that is trig identities then. So I'll see you next time.